Right, so good afternoon. Most people are leaving, that's good. No, I'm just kidding. Um, I know it's too late. I'm going to keep it brief, very short presentation. But I wanted to let you all know initially what NEX is all about. It's a NASA Earth exchange. And we initiated NEX, it's almost for the last, I think, we've been doing activities under the umbrella of NEX for the last 6 to 7 years now. A lot of projects are being funded from NASA, and it's under the same umbrella. Now, what is NEX-AI? And I'm sure all of you here are familiar with machine learning and artificial intelligence. Just raise a few hands if you're aware of what artificial intelligence is. All right, perfect. So I'm not going to go too deep into the technicalities of what kind of algorithms or high-end architectures that we are using as part of artificial intelligence. But what I wanted to start here with this slide is it's again a collaborative effort. We have several people working under the umbrella. We have university colleagues, we have industry mentors, and because it's growing at a very rapid pace, we need to embed this innovation that's happening in the artificial intelligence world, and then kind of use our kind of science data sets that we have and extract features out of it. So as part of NEX-AI, and I call it Data-Driven Insights in Earth Sciences, we have a whole lot to do. We have knowledge, we have collaboration, we have several applications, and we have a load of data sets, right? And these data sets, when I remember when I was starting my PhD work at Boston Universities, we were dealing with data sets at resolutions of like 8 kilometers, and this was from the advanced very high resolution data set. And then came MODIS, which was a very successful NASA mission, and it had Terra and Aqua. And then we were using MODIS data sets for doing a lot of stuff, including anomaly detection, finding water bodies, doing land cover classification. And land cover classification was very big for us. It has a profound importance for a lot of applications, including water resources, for carbon sequestration, for mapping biomass and carbon at national scales, or even at global scales. Now what we thought is, okay, let's go move forward. And then we had the whole Landsat archive available to the people. So people started analyzing Landsat data sets, 30-meter spatial resolution. And what we saw is that it presents us with a lot of problems and issues dealing with Landsat data. And then slowly people started developing these physical algorithms which you could actually deploy to find patterns from these data sets. And then came the whole generation of high-resolution data. And this was essentially started from the commercial world. We had satellites like Digital Globe, Worldview 1, Worldview 2, Worldview 3, all sorts of commercial satellite data sets. We had very high-resolution airborne data sets from a lot of government partners, from USDA, from US Forest Service. And then the important question was, could you actually translate these algorithms that you have developed in coarse resolution data sets and then kind of learn the algorithm in high resolution? And that was the question that we were trying to address. And I think I'm going to show some of the examples that we have been doing, briefly talk about the algorithm part of it, and then how we are trying to implement these algorithms over large data sets. Next slide. So again, it's important to know the mission and vision for NASA Earth Exchange. And we call it Science as a Service. We have several collaborators. Mostly, we are essentially helping scale NASA projects that are being funded to different institutions. We have been kind of successful in actually showcasing some of the activities. And in general, we're trying to create this centralized facility where you have access to data, you have access to models, you have access to codes, you have access to reproducible workflows that is becoming very popular nowadays. And we're trying to make this available to the scientific community. And we have been very successful actually supporting a lot of NASA projects. Next. And just to mention, the whole NASA Earth Exchange facility is residing at the Pleiades Supercomputing at the NASA High Performance Computing Center at NASA Ames. So we have access to supercomputing, and that actually enables us to scale our algorithms. Now, people have been talking about artificial intelligence and specifically deep learning. So when I asked you the question, how many of you know artificial intelligence, a lot of you raised your hands. How many of you actually know deep learning? All right, a couple of you. So there's nothing special in it. I wanted to give a brief introduction of where this comes from, and I think this is very important to us. So this notion of deep learning essentially comes from a lot of domain expertise. People have devoted a lot of time in areas of pattern recognition, in areas of texture recognition, in areas of feature learning for a long, long time. And I remember almost 15 years back, or even 20 years back, when I was doing my master's thesis, I was actually doing a very interesting problem. I had this crab, crabs in the fluvial plain, in the ocean plain, and the crabs actually dig burrows in the sand. And you then put wax, molten wax, on those burrows, and then they create this nice little structure. And we used to take out those essentially molten wax kind of shapes and decipher on what kind of crab environments you have in river plains or in ocean. Now, what I was doing was essentially applying a bunch of Gabor filters. These are essentially spatial filters. And think of it as like if I give an image to you and you essentially multiply that image with a specific line or a curve, it results in a feature for you, right? And we have been applying these Gabor filters to identify patterns. Now, you can construct these spatial filters in a lot of different ways. You can have several of those features actually created by doing discrete operations. Like I could do frequency transform, I could do a bunch of texture representations of the same image, and I could end up having almost hundreds of features, right? Now, let's do it in an automated manner. I give you an image, I give you all the bands, because whenever we're talking about satellite image, we have multispectral bands. And we're talking about red, green, blue, near infrared, shortwave infrared, far infrared, middle infrared. So let's assume we have 7 bands, stacking them up as an image, and we actually convolve the spatial filters with the bands, and that will end up giving you some high-level representation of features. And when I talk about the deep learning architecture in this slide, all I'm trying to say is I have this input. I have a bunch of layers. What it essentially does is convolves the spatial filters with the specific bands and then creates these high-level features. I call it the encoder stage, and then I have a decoder stage which actually decodes it back. So I have to upsample the image. Whenever I'm convolving the spatial filters with the image, I'm actually reducing them because I'm doing some operations like max pooling, which essentially says that if you have 4 pixels, take the maximum value from the 4 pixel and construct one value which is representation of that feature. Now I have to do this decoding because I have to eventually get back to the same image dimension which I'm starting with. So the decoding stage essentially, all it does is takes this feature space from the encoding stage and then multiplies it going upwards. Now, this is a very high level explanation of what architecture that we are using for solving a very specific problem, and this is image segmentation. And there are ways of defining this. When we talk about image classification, we talk about image segmentation or object detection. These are all 3 different things. When you're talking about classification, we're always talking about pixel level classification. And we're talking about segmentation, we're talking about segmenting the whole patch, right? And then we're talking about object detection. We're not essentially segmenting the patch, but we are detecting where that object is. Next slide. So this is kind of a framework that we have been building as part of NASA Earth Exchange. So you have a lot of data sets from different missions, from airborne acquisitions, from new missions that are coming up. And where we try to invest most of our time is creating this training database, and we call it SatNet. And we have been doing this for the last 5 years now. We first published our paper in, I think, 2013, where we used something called deep belief network, or the notion of restricted Boltzmann machine. I know it's getting too technical, but when we started doing this, we wanted to apply these deep neural network architectures for image classification. And that's when we started creating these labeled data sets. And these are hand-drawn polygons, essentially, not just saying that whether it's a grass or a tree, but these are hand-drawn polygons, essentially. And this takes a lot of time. So what you see here are essentially hand-drawn polygons. We have a lot of these labeled data sets for different classes. And when I was mentioning about land cover classification, a very important project which started almost, I think, 6 years back was to support the NASA carbon monitoring system. And the mandate was that we were creating this global scale or continental scale biomass maps, and these are above ground biomass maps. And why do we need to create these maps? Essentially, you saw the last presentation, he was talking about carbon emission. Now, to offset this carbon emission, you need to accurately give estimates of forest cover, where the forests are, because they are sequestering all the carbon. And you also need to measure changes in forest sequestration, carbon sequestration. Now, what we found out as part of this carbon monitoring system effort is we were creating these maps at 30-meter resolution using Landsat and blending other data sets like MODIS. We realized that there is a high uncertainty in the land cover classification that we're using from Landsat. So we thought that we need higher resolution data sets to actually give you a very fine-grained, detailed, map for forest. And that's when we started actually creating these labeled data sets. This is all from the USDA airborne imagery, that is NAPE imagery, National Agriculture Imaging Program. They image the whole of continental US almost every 2 years and provides a wall-to-wall map of 1 meter RGB NIR imagery for the whole of US. So we took that imagery, and it took us quite a bit of time to get it ingested into our system here. Once we had that, once we created that labeled data set, we thought of few applications, right? One is, again, I was talking about image classification and image segmentation. So we had this feature-enhanced deep belief network, which we started off. And then we started using convolutional neural network. The slide which you saw before is actually an encoder-decoder convolutional neural network. And you could also do image super resolution. So you could take something like Landsat and bring it down to 1 meter, from 30 meters to 1 meter, using features from other data sets. And then what we started doing was creating these frameworks. Now, people have been using these open source frameworks to implement some of these algorithms. So what we did was, yes, obviously we do use Keras, we do use a lot of Python, we do use TensorFlow, but then eventually how do you actually scale it up to the cloud, right? And that's where we use something called Apache Mesos and containers. So containers are essentially packaging all your tools and libraries into one single lightweight architecture, which you could actually scale it to a cloud or a high-performance computing. So we use Mesos and Docker to actually package all of this, and then you can easily deploy it on whether it's Amazon Web Services or Google Cloud, or even using any kind of a native high-performance computing infrastructure. Next slide. So this is the first ever high-resolution 1 meter tree cover map that we created as part of the carbon monitoring system effort. I'm really proud, actually, of this map because I come from an image classification background for a long, long time. And when I see this map in front of me at 1 meter, this is really giving me a lot of insights. I won't go into too much details here, but when you're talking about Pacific Northwest, there are a whole lot of forests where there's a lot of logging that happens. Urban forests, that's a big thing for us, right? When you're talking about sequestration, when you're using something like maps derived from Landsat, urban doesn't even show up. So you need to create those pictures of urban forest cover where you could see the trees in your backyard. And you could see some issues here in the map. That's actually the NAPE data that came from 2012. We're actually replacing those tiles with the new NAPE data from 2013. But overall, this looks pretty good. The algorithm can be generalized. That's the best part of deep learning, that when you use a training data set and then train the algorithm, you could actually generalize it to a different area completely. And you could also transfer learn the algorithm. Next map. Next. Okay, sure. This is another application where we have been using the same algorithm, and we call it DeepSat. And for rooftop detection, this was also a very important problem for me because we have been designing the specialized filters called L-shaped filters, and then we apply it with encoder-decoder architecture that we have to accurately delineate the rooftops. Most results you see won't do that properly because you end up having blobs. So what the blue rectangle shows you is the segmented map, and the base layer is an RGB from a digital globe imagery. We were doing this over an open source data set from SpaceNet, and that actually gives you high resolution data set. This is one of our other applications where we're trying to use a bunch of data sets from different satellites and then use our ensemble deep learning architecture to create these baseline climate layers for precipitation, temperature, and then solar radiation using training data from different weather station networks, from different satellite data. And we are going to release this data soon. This is daily 1 kilometer climate baseline layers from 1979 to present. I think this will be very useful for a lot of the scientific community who actually uses this kind of data sets. Next. This is another activity that I'm undertaking with my colleague Prabhat at Lawrence Berkeley Livermore Lab. And this is all about extreme event detection. I don't know if you went to his talk yesterday, but all we're trying to say here is we could use some of these object detection techniques to actually decipher where we have tropical cyclones, where we have atmospheric rivers, and where we have other important weather fronts. Now, it's good to detect these events, but we would also like to really segment these events and then see how these events actually propagate across spatial time. Moving forward. So that's where we are trying to create this framework again, where we are ingesting all of the geostationary data from the new geostationary GOES-16 platform. And this is actually an image from the equivalent, kind of very similar platform that's on the Eastern Hemisphere. This is the Himawari platform. It's the same sensor. And then what here it shows you is it actually can give you imagery every 5 minutes or every 2.5 minutes of the same snapshot. Different snapshots. And that's a lot of imagery you're ingesting, right? Of every 5 minutes, imagine the continental US. And then if you could somehow deploy these rapid, fast, efficient segmentation algorithms to segment clouds and see where they're moving. That's a simple example that I wanted to show you in the next slide. This is where we have some initial results where we are trying to use our DeepSat algorithm, which is essentially the framework that I was explaining. And this is an image RGB base map of the Himawari platform. And that's our segmentation directly from the algorithm, right? So we have these dense clouds, which are white, and then we have these low-level clouds, which are green. Now, I could say that we could use a lot of our physical algorithms to do this kind of simulations, but it takes a lot of time. We are processing these frames every 4 milliseconds. The algorithm takes 4 milliseconds to actually create this segmented map. Now, that's where the beauty of using these architectures, and it's not that something we are doing. It's not that we are doing something really hard and then something which we cannot understand. I mean, the community has been kind of embedding these architectures in different applications. You just have to think where the suitable applications are. And I think this is where we could start now tracking these clouds almost every 4 milliseconds, because 4 milliseconds is nothing in terms of processing time. So if you could actually apply these algorithms in real time, that would give us a lot of benefit. Next, please. So this kind of gives an overview of where we started. A last slide, which you guys can kind of keep looking, but we started in 2013. We were doing this 1 meter tree cover classification, and then we started kind of enhancing our labeled data sets. Without good labels, you simply cannot implement these algorithms. And this kind of gives you a timeline of where we are in terms of new publications that are coming up, or in terms of new research that we're doing as part of NEX-AI. Thank you.